This video will summarize the various types of integrals and integration techniques learned in Chapter 7. First, I need to emphasize that you should always check for the basic substitution techniques that we learned first semester, including long division, multiplying by the conjugate, and other things learned in Chapter 4 and Chapter 5. To begin, I'm going to start with some of the basic techniques that were reviewed in Section 1. If you see something like a fraction in the first one technique we learned, especially when there are trig functions, is to multiply by the conjugate. So I'm going to multiply numerator and denominator by cotangent t plus cosecant t. And if I multiply this out, I get cotangent t plus cosecant t in the numerator. In the denominator, I have cotangent square t minus cosecant square t. Then what you want to try to do is apply one of the Pythagorean trig identities. We know that 1 plus cotangent square t equals cosecant square t. So rewriting this means that cotangent square t minus cosecant square t would equal negative 1. So I can rewrite this integral as cotangent t plus cosecant t all over negative 1 dt, which means basically all I'm integrating is negative cotangent t minus cosecant t dt. You are responsible for remembering all the integrals that we learned in first semester, so the antiderivative of negative cotangent t is natural log of the absolute value of cosecant t plus the natural log of the absolute value of cosecant t plus cotangent t plus c. In the second example here, notice if I let u equals 7 plus e to the negative 2x, and then take the derivative, I get du dx equals e to the negative 2x times negative 2 for chain rule, and therefore du equals negative 2 e to the negative 2x dx. But notice in the numerator there is no e to the negative 2x to satisfy my du. So instead of doing this, we're going to use a different technique. So basically we need some e's in the numerator to satisfy our du when we do u substitution. To do that, we're going to multiply numerator and denominator by e to the 2x. By doing so, we get 5e to the 2x dx in the numerator. In the denominator, when we distribute, we get 7e to the 2x plus 1, because e to the negative 2x times e to the 2x is 1. Now, if we let u equal 7e to the 2x plus 1, and take the derivative, we get du dx equals 7e to the 2x times 2. And solving for e to the 2x dx, we get 1/14 du. So now I can rewrite this integral as 5 times 1/14 du, all divided by u, making the antiderivative 5/14 natural log of the absolute value of u plus c, and then replacing the u, we get 5/14 natural log of the absolute value of 7e to the 2x plus 1 plus c. Some of the other basic techniques reviewed in Section 1 included long division, just multiplying it out, and of course regularly used substitution, where typically you let u equal the inner function, or in the case of a radical, sometimes you let u equal the radicand. Now moving on to the techniques that were new in Chapter 7. The first thing we learned was integration by parts, where we often have something like a polynomial times an e function or an inverse or a trig function. We have our inverse trig functions. And this was the formula that was basically u times v minus the integral of v du. So I'm going to demonstrate it with these three examples. And the first one is the classic case where you let u equal the polynomial. And that's usually the first place to try. So we're going to let u equal 2x minus 3. And then if you take the derivative of that, du dx equals 2. So du equals 2 dx. The rest of our integral is going to be our dv part. So dv equals e to the 5x dx. And integrating both sides, you get e equals 1/5 e to the 5x plus c, but we always save the c for the very end. The formula for integration by parts was the integral of u dv equals uv minus the integral of v du. So substituting this in, our u is 2x minus 3, our v is 1/5 e to the 5x, minus the integral of v, 1/5 e to the 5x, times du, which is 2 dx. Consequently, through integration by parts, half of our integral is completely solved now. 2x minus 3, 1/5 e to the 5x. The remaining integral is easier to solve because there's no polynomial in the way. So we have minus 2/5, which is our multiplier, and then integrating e to the 5x, you get 1/5 e to the 5x. And now we put in our plus c. So the final answer is 2x minus 3 times 1/5 e to the 5x minus 2 over 25 e to the 5x plus c. In our second example of integration by parts, now we're going to have an inverse trig function. So instead of letting u equal the polynomial, in which case there actually is no polynomial, we're going to let u equal the inverse trig function. So u equals arc cosine of x over 2. And taking the derivative of that, du dx is going to equal negative 1 over the square root of 1 minus quantity x over 2 squared. And then multiplying by chain rule, we need to multiply by a half. All that leaves for our dv then is dx. And so if we integrate both sides, v is going to equal x. So in our formula uv minus v du, we have arc cosine of x over 2 times x minus the integral of v, which is x, times du, which is negative 1 over square root of 1 minus x over 2 squared times 1/2 dx. So multiplying this dx over here. If we simplify this, before integrating, we have x arc cosine of x over 2 plus 1/2 the integral of x over square root of 1 minus x over 2 quantity squared. Now we're going to go ahead and do a regular u substitution, because if we let u equal 1 minus x squared over 4, which is our radicand, then the derivative du dx equals negative 1/2 x. And notice I have an x in the numerator that I can then solve for. So negative 2 du equals x dx. So substituting in, I have my x arc cosine of x over 2 for my parts, plus 1/2, and now replacing all this, I'm going to have a negative 2 du for the x dx part, all over square root of u. But this can be rewritten as x arc cosine of x over 2. I'll go ahead and make this a minus u to the negative 1/2 du, which I can integrate by undoing the power rule. So x arc cosine of x over 2 minus 2u to the 1/2 plus c, and then substituting the u that I used in this particular substitution, the final answer is x arc cosine of x over 2 minus 2 times the square root of 1 minus x squared all over 4 plus c. The final one I'm going to do here is the one that we saw way up here. I'm going to go ahead and drag it down. And this is the one you can recognize, if you recall from what we did in class, where we do parts twice and you end up with what you start with. And then you add it over to the other side and turn it into an algebra problem. So that's what I'm going to do next. Remember, in these particular problems, it didn't matter what you let u equal to u or dv as long as you were consistent the second time and didn't undo the derivative that you did the first time around. So for this case, I'm going to let u equal e to the negative 3x. And I will let dv equal sine 4x. So if I do my derivative, I'm going to get du dx equals e to the negative 3x times negative 3. And so therefore du equals negative 3 e to the negative 3x dx. If I integrate my v here, I'm going to get 1/4 to undo the for the u substitution part, negative cosine of 4x. So, substituting this all in, I'm going to get u times v, which is negative 1/4 cosine of 4x, minus the integral of v, negative 1/4 cosine of 4x, du, which is negative 3e to the negative 3x dx. And I'm going to go ahead and simplify this before I do my next parts. So the first term is negative 1/4 e to the negative 3x cosine 4x. Distributing this, I have 3 minus signs, so that becomes minus 3/4 integral of e to the negative 3x cosine 4x dx. And now I'm going to do my second part. So since I let u equal the e function the first time, I'm going to let u equal the e to the negative 3x function the second time. And that means my du will be again negative 3e to the negative 3x dx. The second time around, I'm going to let dv equal cosine 4x dx. And therefore integrating, v is going to equal positive this time, 1/4 sine of 4x. So substituting in, I get negative 1/4 e to the negative 3x times cosine x, or sorry, cosine 4x from the first part, minus 3/4 my next part. So my next part again is u times v, 1/4 sine of 4x, minus the integral of v, 1/4 sine of 4x, du, which is negative 3e to the negative 3x dx. And then again, I'm going to distribute this out. So we have a negative 1/4 e to the negative 3x cosine 4x. Distributing the next term, I have minus 3/16 e to the negative 3x sine 4x. And then distributing the last term, I have 3 minus signs. So minus the integral of 9/16, because I have a 1/4, a 3, and a 3/4. Integral of e to the negative 3x sine 4x dx. Now, if you recall, all of this equaled the original integral, which was e to the negative 3x sine 4x dx. So what I'm going to do is basically add this over to the left side of the equation. So I have one integral plus 9/16 of an integral. That makes it 25/16 of my integral e to the negative 3x sine 4x dx. equals negative 1/4 e to the negative 3x cosine 4x minus 3/16 e to the negative 3x sine 4x. And last step is to divide both sides by 25/16. So treating it like an algebra problem. And so my final answer for e to the negative 3x sine 4x dx is 16/25 times the quantity negative 1/4 e to the negative 3x cosine 4x minus 3/16 e to the negative 3x sine 4x plus c. With these, remember to be careful with your distribution, checking that you actually completely distributed through the fractions as well as the negative signs. So hopefully I didn't make a mistake here either. The next section in Chapter 7, we talked about using trig identities to simplify integrals into something that we could integrate, typically with u substitution. So I'm going to be walking through each of these one at a time to illustrate them. Let's start by moving some of these over so that you can worry about them later. Alright, so sine to the fifth 3 theta. We talked about using the Pythagorean identities and rewriting this so that you have a part that's our u and then the other half that's going to be our du. With the odd sines and cosines, probably the first place to start was typically to move aside one of the sines or cosines. In this case, we'll move aside a sine 3 theta d theta. And then the remaining sine to the 4th theta, we can rewrite using our trig identities. Cosine squared plus sine squared equals 1. So sine squared equals 1 minus cosine squared. And in this case, it's going to be 1 minus cosine squared 3 theta squared to make it sine to the 4th. If I multiply this out, you get 1 minus 2 cosine squared 3 theta plus cosine to the 4th 3 theta. We have this extra sine 3 theta on the side, d theta. Now notice if I let u equal cosine of 3 theta, and I take the derivative, I get du d theta equals negative sine 3 theta times 3. So solving for sine 3 theta d theta, negative 1/3 du equals sine 3 theta d theta. So everywhere there's a cosine, I'm going to replace it with a u, and the sine 3 theta d theta at the end, I'm going to replace with a negative 1/3 du. So now I have 1 minus 2u squared plus u to the 4th, negative 1/3 du. If we integrate this, I'm going to go ahead and put the negative 1/3 on the outside. I would get u minus 2/3 u cubed plus 1/5 u to the 5th plus c. So the final answer for this is going to be negative 1/3 u, which is cosine of 3 theta, plus 2/9 u cubed, so cosine of 3 theta cubed minus 1/15 u to the 5th, so cosine of 3 theta to the 5th plus c. However, you couldn't use that technique if it was only even powers. So something like sine to the 4th 3 theta, you can't remove a sine because a sine to the 3rd power would require a square root if you simplify it using Pythagorean identities. So instead for this one, we're going to use this identity here, which comes from the double angle identity for cosine 2, 2. Sine to the fourth is the same as sine squared squared. So I can rewrite this as 1/2 minus 1/2 cosine. Now this is from the double angle identity, so 2 becomes 2t. So in this case, 3 theta is going to become 6 theta squared d theta. Multiplying this out, you get 1/4 minus 1/2 cosine of 6 theta plus 1/4 cosine squared of 6 theta. The first two terms can be integrated fine. The last one being a cosine squared, we're going to use the other half formula, which was cosine squared t is 1/2 plus 1/2 cosine 2t. So now this integral becomes 1/4 minus 1/2 cosine 6 theta plus 1/4 times the quantity 1/2 plus 1/2, and again I'm applying the double angle identity, so this becomes cosine 12 theta. Integrating all these pieces, we're going to have 1/4 theta minus 1/12 sine 6 theta plus 1/8 theta plus 1/8 and also a 1/12 sine of 12 theta plus c. So 1/4 theta minus 1/12 sine 6 theta plus 1/8 theta plus 1/96 sine of 12 theta plus c is our final answer. That's what you typically do with sines and cosines. Now we're going to look at these three here. We'll look at tangents, we'll look at some cotangents, and I'll save this one also for later. So with the tangents and secants, you need to remember your derivatives for secants, tangents, cotangents, and cosecants, and that way you know what to set aside and what to try. For example, if we try to let this equal secant squared, let's say. So we have a tangent 3 theta, we have a secant theta, and then we have a secant squared theta d theta. So then our task will be to rewrite this in terms of tangents. But the identity is 1 plus tangent squared equals secant squared. So secant theta would have to be square root of 1 plus tangent squared, which is not easy to work with because you can't distribute into a square root. So instead, you want to try the other one, which is to put aside a secant theta tangent theta, and then rewrite the rest in terms of secants. So for the rest, we have tangent squared theta, we have secant squared theta. And now we need to rewrite this in terms of secants, which is easier because 1 plus tangent squared is secant squared. So tangent squared is secant squared theta minus 1. So if you distribute this out, you get secant to the 4th theta minus secant squared theta, secant theta, tangent theta, d theta. And now if you let u equals secant theta, the derivative of u, du d theta, equals secant theta tangent theta. So that means du equals secant theta tangent theta d theta. So all of this here I can replace with a du, meaning my integral is now u to the 4th minus u squared du. Integrating, you're going to get 1/5 u to the 5th, so 1/5 secant theta to the 5th, minus 1/3 u cubed, so 1/3 secant theta cubed, plus c for our final antiderivative. Over over here, we're going to do something with cotangents and cosecant squareds. So notice if I take out a cosecant theta, cotangent theta, d theta, I'm left with a cotangent cubed theta, which is hard to rewrite into cosecants because it's not an even power. So instead, we'll set aside a cosecant squared theta, d theta, and the remaining integrand I have cotangent to the fourth theta. I have cosecant squared theta, and I need to basically rewrite this into cotangents. So cotangent to the fourth theta. Cosecant is 1 plus cotangent squared theta. Cosecant squared theta, d theta. This time distributing, I'm going to have cotangent to the fourth theta plus cotangent to the sixth theta. Cosecant squared theta, d theta. If I let u equal cotangent theta, then the derivative is going to be negative cosecant squared theta, d theta, for the differential. And now if I substitute, I have u to the fourth plus u to the sixth, and then this would be cosecant squared theta, d theta, would be negative du. So the antiderivative of this would be negative 1/5 u to the fifth plus 1/7 u to the seventh plus c. And then substituting in the original function, negative 1/5 cotangent theta to the fifth minus 1/7 cotangent theta to the seventh plus c. I'm looking back up here. Tangent squared, secant squared, secant tangent, secant to the fourth minus secant squared. I think that's correct. Okay. Last one I'm going to do with our trig identities is this one here. Whoops. Let's try that again. So this particular one here, I taught it actually in the second section when we did integration by parts, because you can actually do parts twice and work it out. If you want to do parts twice, what you would do is you would let u equal, say, sine 7x the first time around. You would let dv equal sine x. And then the second time around, you would let u equal cosine 7x because you'll be working with the du. And then you would let dv equal the cosine x. So basically keeping this coefficient consistent, whatever you let u equal as a result. Now I put it in the trig identities part because a lot of people prefer the trig identity to doing this one. And so that's what I'm going to review instead. To do it using trig identities, you need to remember the trig identity that involves sine times a sine, which is the cosine a plus b identity. So in this case, we're going to do cosine of 7x plus x, which would be cosine minus sine. And then if we do likewise with the cosine 7x minus x, we're going to do cosine plus sine. So notice I have the sine 7x's over here on this side. You need to think about how you want to combine these so that the result, after you combine them, is a sine 7x times sine x. So if I subtract these, I'm going to get cosine of 8x, because technically this is an 8x, minus cosine of 6x. If I subtract, those two subtract away, and I get negative 2 sine 7x sine x. So dividing both sides by negative 2, now I know that sine 7x sine x is equivalent to negative 1/2 cosine 8x plus 1/2 cosine 6x. So this particular integral, sine 7x sine x dx, I can rewrite as negative 1/2 cosine 8x plus 1/2 cosine 6x dx. Minus, right? No, plus. And now if I integrate that using u substitution, I get negative 1/16 sine of 8x plus 1/12 sine of 6x plus c. I'm just going to double check. So I subtracted. So cosine 8x minus cosine 6x divided by negative 2. So negative 1/2 plus 1/2. And then integrating negative 1/16 plus 1/12. A third technique we looked at was trigonometric substitution. This was typically used if you had a radical, because then if you use your Pythagorean identities, you can actually simplify the radicand to one term and therefore cancel out the square root sign. So I'm going to look at 3 different problems. Let's start with the one on the left. So something squared minus 1. You have the identity 1 plus tangent squared theta equals secant squared theta. Or in other words, tangent squared theta equals secant squared theta minus 1. So I'm going to use that identity here since I have a minus 1. I'm going to let x equal secant theta. So everywhere there's an x, I'm going to replace with secant theta. I also need to replace the dx. So taking the derivative, dx d theta equals secant theta tangent theta. So solving for the differential dx, you get secant theta tangent theta d theta. Substituting all of this into the integral, I'm going to have secant squared theta minus 1 to the 1/2. I have a secant theta tangent theta d theta. And in the denominator, I have x to the 4th, which is secant to the 4th theta. So we're going to simplify this. Secant squared minus 1 is tangent squared to the 1/2 is tangent theta. I have a secant theta, which actually I will cancel with one of those. So now I have tangent squared theta d theta in the numerator, and I have secant cubed theta in the denominator. When in doubt, you should always change back into sines and cosines. So this would become sine squared theta over cosine squared theta times 1 and cosine cubed theta in the numerator. That means a lot of the cosines cancel out, and we have sine squared theta cosine theta d theta, which actually integrates very nicely with u substitution. So if I do the u substitution and let u equal sine, the derivative is cosine. So that means the antiderivative of this is 1/3 sine cubed theta, that's a cube, plus c. Now we need to return to our original variables. So if you look at the original setup, x was equal to secant theta. That means in a triangle, a right triangle, if I label this theta, the secant ratio would be x. Secant is hypotenuse over adjacent. The remaining side of my right triangle then would be x squared minus 1. So substituting in for this, I have 1/3 sine of theta. Sine is opposite, so square root of x squared minus 1 over hypotenuse cubed plus c. Now let's try the one over here on the right. First, I need to get this set up so I can use the Pythagorean identity. So instead of 9 minus, I want this to be 1 minus. To do so, I'm going to factor out a 9 from the square root, which comes out as a 3. And then the remaining radicand is going to be 1 minus 25x squared over 9 dx, which I can rewrite into the integral of 1 minus 5x over 3 squared dx. So this one we're going to use sine because 1 minus sine squared is cosine squared. So we're going to let 5x over 3 equal sine theta. And then I'm going to solve for x, so I can solve for what dx is by taking the derivative. So x equals 3/5 sine theta. Dx d theta equals 3/5 cosine theta. So dx is going to equal 3/5 cosine theta d theta. And I need more room. Alright, so substituting in, I have 3 square root 1 minus sine squared. I need an integral sign. My dx is 3/5 cosine theta d theta. Simplifying that, you get 9/5. 1 minus sine squared is cosine. 1 minus sine squared, I'm sorry, is cosine squared, but square rooted is cosine. I have another cosine. So that becomes cosine squared theta d theta. This is when we use the identity that we learned with the trig identity section. So cosine squared is 1/2 plus 1/2 cosine 2 theta. And then integrating that looks like it's going to be 9/10 theta plus 9/10 cosine 2 theta plus c. But if I draw my right triangle, I think I said that sine theta equals 5x over 3. So that would be opposite over hypotenuse. And, whoops, I can't get, that's the wrong antiderivative. This antiderivative should be sine. I can't get sine 2 theta out of that triangle. So instead, we're going to use another trig identity. Sine 2 theta is 2 sine theta cosine theta. Now we can substitute. So we have 9/2 theta. Theta is going to be the arc sine of 5x over 3. Plus 9/5, I'll go ahead and multiply the 2 and the 9/10. Sine theta, which is 5x over 3. Cosine theta, which is going to be my missing side, 9 minus 25x squared. So square root of 9 minus 25x squared, all over the hypotenuse, 3 plus c. Basically, with the trig substitution, you have 3 parts. You substitute in your theta, you integrate it with whatever trig techniques you need, and then you use the triangle to return it back to the original variable. Now, the last one that we're going to do, this way I can take care of all 3 different substitution functions, is x dx over the square root of x squared plus 10x plus 41. So again, you have a radicand, which is a radical, which is your clue that you're going to use your trig substitution. And in this case, to get it into something squared, we're going to complete the square. So x squared plus 10x plus 25 completes the square, plus 16 left over that doesn't get used to complete the square. So factoring this becomes x dx over the square root of x plus 5 squared plus 16. And then factoring out the 16, 1/4 x dx over the square root of x plus 5 over 4 squared plus 1. So we're going to let x plus 5 over 4 equal tangent theta this time. Because 1 plus tangent squared is secant squared theta. So that means x equals 4 tangent theta minus 5, which means in place of dx, we're going to replace it with 4 secant squared theta d theta. Substituting, we have 1/4. We have an x I need to replace this time. So 4 tangent theta minus 5. Dx is 4 secant squared theta d theta. And the denominator was 1 plus tangent squared, which is secant squared. Square rooted becomes secant theta. Alright, so let's simplify this. The 4's cancel out, one of the secants cancel out, and so if I distribute this, I get 4 tangent theta, secant theta, minus 5 secant theta, d theta. Integrating is 4 secant theta, minus 5 natural log of secant theta plus tangent theta, plus c. And now for our triangle. So here's my theta. Tangent is opposite over adjacent, making the hypotenuse x plus 5 squared plus 16. So substituting everything in, I have 4 secant theta, which is the square root of x plus 5 squared plus 16 all over 4, minus 5 times the natural log of secant theta, square root of x plus 5 squared, plus 16 all over 4, minus tangent theta, x plus 5 over 4, plus c. Okay, now we have one more major technique that we learned, which was partial fractions. Partial fractions, your clue is basically you want to see if the denominator factors. If it factors into several pieces, then you can think of it as separate fractions that might be able to be combined to be the one that you're looking at as the original problem. So in this particular case, over on the left, I can factor this just a little bit more into x minus 1 and x plus 1 squared. So you want to consider all the possible ways the denominator could be that we get a common denominator of x minus 1 and x plus 1 squared. So the factors would be a over x minus 1. You could have b over x plus 1 squared. But technically, you could also have c over x plus 1, which is called the degenerate case. And again, if I were to get a common denominator of these three, the common denominator would still be x minus 1 times x plus 1 squared. Now to solve for a, b, and c, we're going to find that common denominator. So if the common denominator is x minus 1, x plus 1 squared, a would need to be multiplied by x plus 1 squared. B would need to be multiplied by x minus 1. And c would be needed to be multiplied by x minus 1 and x plus 1. That would get us a common denominator, and then this is our numerator for x minus 1, x plus 1 squared. And this has to equal my original, which was x squared over x minus 1 times x plus 1 squared. This means my numerators have to match. So a x plus 1 squared plus b times x minus 1 plus c times x minus 1, x plus 1 has to somehow equal x squared. So I need to find the values of a, b, and c to satisfy this equation. One technique we talked about was substituting in values of x to solve for a, b, and c. So if we substitute in x equals 1, we get a times 2 squared, which is 4, plus 0 equals 1. So a equals 1/4. Substituting in x equals negative 1, we get a times 0 plus b times negative 2 plus c times 0 equals 1. So b equals negative 1/2. Now there's nothing as nice to substitute in to solve for c. So another technique we talked about was looking at coefficients on both sides. If I were to multiply out the left side, the coefficients for x squared would be ax squared plus cx squared, and that has to equal x squared, which means basically looking at just the coefficients, a plus c has to equal 1. Now I know a equals 1/4 plus c equals 1, so that means c has to equal 3/4. And now I have my three missing coefficients. That means this integral can be rewritten as 1/4 over x minus 1 minus 1/2 over x plus 1 squared plus 3/4 over x plus 1. And now integrating each of these pieces, would be 1/4 natural log of the absolute value of x minus 1 plus 1/2 over 1 over x plus 1. And that's because it's not a natural log, that's just a power rule. That's like x plus 1 to the negative 2. So the antiderivative would be negative x plus 1 to the negative 1. Plus 3/4 natural log of the absolute value of x plus 1 plus c. I'm going to move this one down here so I don't have to cramp on space. For this one, I went ahead and factored it out to talk about something else. So notice in this one, I have a quadratic in the denominator, and it can't be reduced and factored anymore because it's a sum of squares, it's not a difference of squares. So our partial fractions are going to be a over s for the first factor. To make this quadratic, I could technically have an s term in top, and it'd still be a proper fraction form. And then because it is a repeated root, I'm also going to need a ds plus e over the degenerate term, s squared plus 1. So getting a common denominator, a would need to be multiplied by s squared plus 9 squared. bs plus c needs to be multiplied by s. And ds plus e needs to be multiplied by s and also by s squared plus 9. And all of that has to equal s to the 4th plus 81. Alright, so let's start with substitution. Not a lot of places we can substitute, so let's start with s equals 0. If I substitute in s equals 0, I get 81a plus 0 equals 81. So a equals 81. And I think that's, oh, I'm sorry, a equals 1. And unfortunately, I think that's the only thing I can substitute. So then let's look at the powers of s to the 4th. A s to the 4th would be this term here, squared. And then over here I have a ds to the 4th. So plus ds to the 4th has to equal 1 s to the 4th on the right-hand side. But I know a is 1, so that means 1 plus d has to equal 1, so d equals 0. Now I'll go ahead and rewrite this so I have a little bit less to work with. So if I rewrite this, a equals 1, so that'll be s squared plus 9 squared. B and c I don't know yet, so bs plus c times s. D is 0, so then e times s squared plus 9 has to equal s to the 4th plus 81. Okay, so let's see here. Let's do our s cubed terms, because I only see one s cubed term. E s cubed has to equal, there's no s cubed on the other side. So e equals 0. So that turns out. Then if I look at my s squared terms, if I multiply this out, I'm going to have s to the 4th plus 18s squared plus 81 plus bs squared plus cs equals s to the 4th plus 81. So I took care of the s to the 4th and the 81. That means 18 plus b equals s squared, but there's no s squareds on the other side. So b equals negative 18. And there's no s's on the other side, so c equals 0. So my final result for all of this would be a, which is 1. So I've got 1 over s, plus b, which is negative 18, s plus c, but c is 0, over s squared plus 9, squared, s squared plus 9 squared, and everything else is 0. Oh, that simplified a lot nicer than I thought it would. Okay, so integrating this, let's do a u substitution for this. Let's let u equal s squared plus 9. Then du ds is 2s. So 1/2 du will equal sts when I get there. So for the first part, natural log of the absolute value of s minus 18. Oh, I haven't integrated this out yet. So sts, I'll put in 1/2 du. And then s squared plus 9 is u, so u squared. So natural log of the absolute value of s minus 9, and this is like u to the negative 2, so negative u to the negative 1 plus c. So our final answer is going to be natural log of the absolute value of s plus 9 over u, which is s squared, plus 9 plus c. Alright, L'Hopital's wasn't an integration technique, but we then later used it for improper intervals. So remember L'Hopital's, you're looking for all those indeterminate forms before you do it. Like in this case, if you put in x equals 0, you get 1 over 0, which you can almost kind of think of as infinity, minus infinity. But technically infinity is just a big number. They don't have to be equal to each other, which is why we're going to use L'Hopital's to work this out instead. And so what you want to do typically is write it as a single fraction so that you can take the derivative of the numerator and the derivative of the denominator. So the limit as x approaches 0 of 3x sine x plus sine x minus x all over x sine x. And notice if you substitute in x equals 0, you get your 0 over 0 situation, which is your L'Hopital's. So we'll take the derivative of just the numerator, which would be 3x cosine x plus 3 sine x plus cosine x minus 1 all over our product rule. So x cosine x plus sine x. And if we substitute in this time, we get still, I believe, 0 over 0. Which means we're going to do it again. So doing it again, limit as x approaches 0, we're going to get 3 cosine x minus 3x sine x plus 3 cosine x minus sine x, and the derivative of 1 is 0, all over x times negative sine x plus cosine x plus cosine x. And substituting in x equals 0, you get 3 minus 0 plus 3 minus 0 all over 0 plus 1 plus 1, 6 over 2, 3. This one over here, if you substitute in infinity, 1 over infinity is like approaching 0, so this is like our 1 to infinity. Indeterminate form. But again, it's not exactly equal to 1. It's a little bit larger than 1, and so that's why we have to use L'Hopital's to work it out instead. Oops. So for this particular one, what we did was we rewrote it into a different problem, looked at a different problem. We looked at instead at the natural log. So we said, okay, I'm going to look at the natural log of this problem, which was natural log of 1 plus, I'm going to write this as 5/3 x to the negative 1, 2x. Because then we can use the natural log properties and bring the 2x in front. Natural log of 1 plus 5/3 x to the negative 1. And then because we wanted to rewrite this as a fraction, you could rewrite this as 2 natural log of 1 plus 5/3 x to the negative 1. And I can move this x in the numerator down to x to the negative 1 in the denominator. And this is still L'Hopital's, because as x approaches infinity, the second term approaches 0. ln of 1 is 0. 1 over infinity is 0, so it's still our indeterminate form. Now we're going to use L'Hopital's with this. So the limit as x approaches infinity, 2, derivative of natural log is 1 over 1 plus 5/3 x to the negative 1, times chain rule, so that's times negative 5/3 x to the negative 2, that's a 3, divided by the derivative of the bottom, which would be negative x to the negative 2. So these two terms here cancel. And as x approaches infinity, this goes to 0 right here. And so you end up with 10/3. But remember that was looking at the natural log version of it. So our final answer is undoing the natural log. And so our final answer of limit as x approaches infinity of the original problem, which was 1 plus 5 over 3x to the 2x, is going to be e to the 10/3. Now, the whole purpose of L'Hopital's was it came up possibly with the indeterminate integrals. An indeterminate integral is when one of the bounds is not a number, or you have a discontinuity that you're considering instead. For example, in this example on the left, it is not continuous at 1, so technically we can't use the fundamental theorem of calculus because it has to be continuous at both endpoints. So instead, we rewrite it as a limit problem. And basically, this was the one where I stressed notation because you have to make sure you have the integral set up to satisfy the conditions for fundamental theorem of calculus before you can actually do the integral of it. So we set the limit as a approaches 1 from the right because I'm looking at the bound from 1 to 2. And then instead of from 1 to 2, we made this from a to 2. ds over s square root of s squared minus 1. And remember, you couldn't squeeze too many steps together with the improper integrals. So the next step was to evaluate the antiderivative. In this case, it's an arcsecant of s from a to 2. And still doing FTC, the next step would be substituting in the bounds. So arcsecant of 2 minus arcsecant of a. And now you could evaluate the limit because you've taken care of all the FTC stuff. So arcsecant of 2 is like the cosine of 1/2, which would be pi over 3. Minus the arcsecant of a. Well, as a approaches 1, arcsecant of 1 is the same as arccosine of 1. And so that would be 0. And so you get pi over 3 for the final answer there. Over on the right, this is the one going to infinity, and infinity is not a number. So again, you had to rewrite it using limits. So this one we're going to say the limit as a approaches infinity. Now you can only approach infinity from one direction, so you don't need the plus or minus sign. 3 to a, and this one you can see because of factors, we're going to use partial fractions. So this means that a times x minus 2 plus bx needs to equal our numerator, which is 1. Substituting in x equals 2, b will equal 1/2. Substituting in x equals 0, a is going to equal negative 1/2. So I'm going to rewrite this as the limit as a approaches infinity, integral from 3 to a, negative 1/2 over x plus 1/2 over x minus 2. And again, I don't want to evaluate the limit until I've completely taken care of FTC. So limit as a approaches infinity, negative 1/2 natural log of the absolute value of x plus 1/2 the natural log of the absolute value of x minus 2 from 3 to a. Substitute in the bounds, don't do the limits and the bounds at the same time. So negative 1/2 natural log of a plus 1/2 natural log of the absolute value of a minus 2 plus 1/2 natural log of 3 plus 1/2 natural log of 3 minus 2. Now, if you notice as a approaches infinity, I have here pretty much an infinity minus infinity situation. So I need to rewrite that. And we're going to use our log properties. So limit as a approaches infinity of 1/2 natural log of a minus 2 minus ln of a plus 1/2 ln of 3. With that, using log properties, I can rewrite as 1/2 ln of a minus 2 over a plus 1/2 natural log of 3. And as a approaches infinity, this is like our horizontal asymptote idea. Top and bottom degrees are the same, so it approaches 1. Natural log of 1 is 0. So the final answer is 1/2 ln of 3. What you don't want to do is please don't put the infinities in there, because infinity is not a number, so you can't say infinity minus 2. So the final answer here is 1/2 natural log of 3. Take a look at your notes. Look over the handouts. We did many handouts, many practice problems in this unit, and by all means come see me if you have any questions. Good luck studying.